Välkomna
Tack.
till det här seminariet. Vichy ska presentera Methodology Development for Parametric CAD Modeling in CATIA V5 to aid simulation-driven design using turbine volute as a case study. Efter det så ska Niklas opponera på det här arbetet. Och som vi brukar göra så ställer vi inga frågor medan Vichy och opponenten ska hålla på. Vi sparar det till på slutet då. Och när det här är klart då ska jag då meddela ifall arbetet är godkänt eller inte. Vilket är högst troligt att det är godkänt. Spoiler alert. Jag själv heter mig Tarkian. Jag har varit handledare för Vichy och jag jobbar på maskinkonstruktion som adjungerad lektor. Och jag arbetar då inom det här området. Ja, jag kommer skicka iväg den här lappen för er som vill ha det registrerat så att ni har varit på den här examen så får ni skriva upp det här. Resten av det här skriva. Okej. Varsågoda, vi kör.
Det är på engelska då?
Absolut. Kör på engelska. Absolut.
So, okay. Welcome everyone. And so good to see all of you here today. It makes me really nervous. My name is Vichy. I'm here to present my thesis. The presentation of my thesis, which I conducted in Scania for 20 weeks during this semester. And it's about parametric CAD modeling and its relation or its application in simulation-driven design. It's also about a methodology on how to create these kinds of models. This thesis was actually conducted alongside another thesis by Marcus Bloomberg. And for those of you who have already seen that, maybe revisit some elements that we already brought up. And as you already figured out, my presentation will be in English. The outline of my presentation will be the following. I will introduce you to parametric CAD models and its relation to simulation-driven design. And then I'll briefly talk about my background, the purpose of my thesis, and how that transformed into my goals and research questions. Furthermore, I will continue with my theoretical framework, and then I'll talk a little bit how I chose to conduct my thesis before I start presenting my results. And after a brief demonstration, I will finally reveal my conclusions, or the answers to my conclusions. And so after I open you up, we can have some questions and discussion. And the background to why my thesis came to be at Scania is because Scania, as an organization, wants to lower fuel consumption and decrease pollutant emissions while maintaining the efficiency. And however, this is something that their competitors are doing as well, which means that the progress and development in the organization has to progress faster. Looking at the simplified version of the development process in Scania involving simulation, we have the designer working in CATIA, developing non-parametric CAD models, which they then send to CFD or FEM. These disciplines then take the model, perform simulation, and make some minor modifications for optimization purposes. And if the results are satisfactory, the results are documented and reported. However, there is actually no way for the designer to, in a precise way, interpret these modifications. Instead, they have to be visually interpreted and not often in a very accurate way. Even worse, if the results are worse or bad, not satisfactory, the design or the simulation engineer have to go back to the design engineer and ask for a new, heavily modified model. And that takes time because the design engineer have to actually remodel the entire model from scratch sometimes. And so with all these iterations back and forth, the time for each iteration has become an increasing matter. And this has to be, of course, reduced. And so in the end, the design engineers are creating these non-parametric CAD models which are actually not intended for modifications, yet the design engineers are required to do just that, to modify their CAD models. So the question is then, what can be done about that? And in this thesis, it's proposed to use parametric CAD models, and that raises the question, what are parametric CAD models? They are simply models that can be, or they are partly or fully coupled to user-defined parameters, and which gives the user direct control over the shape and form of the CAD model. And since you initially design a model that is designed to be remodeled or reconfigured already in the beginning, they're expected to be much better at being modified. And now you'll see an example model, a camshaft, in an animation of a parametric CAD model. And the most obvious modification is the topological change, lengthwise. And that brings me, or us, to my purpose of this thesis. And the purpose is to investigate the benefits, challenges, and conditions of using parametric CAD models in CATIA V5 for aiding CFD simulation and optimization in the development of engine components. And with the purpose defined, my goals are to simply develop a methodology for creating these parametric CAD models from the designer's point of view. And these CAD models have to be robust, flexible, comprehensible, and intelligent. Whereas intelligent means to create models that can adapt automatically to design requirements or geometrical constraints. Another goal of mine is to parameterize a component in a case study as a proof of concept. And the component that was chosen to be parameterized is a the internal gas volume of a twin scroll turbine volute. And this is the pink part of this assembly. And actually this component is, the design-wise, it's very limited, the knowledge about it is quite limited at the organization because the responsibility of developing and manufacturing it is fallen to their subcontractors at Scania. And finally, the research questions in my thesis are four. The first being, what are the benefits of using parametric CAD models? Second, in what instances are parametric CAD models compatible in the design phase? When is it not? What are the challenges of creating and using parametric CAD models? And lastly, how should Scania work with parametric CAD models? Now the last one is actually quite essential because I didn't want to develop a methodology that was not connected or not taking into account the organization itself. Instead, I wanted to develop a methodology that respected and in the end could fit in the design process at Scania. Moving on to my theoretical framework, I started actually looking at how parameterization is defined and how different levels or different manners of categorization, different manners of parameterization are categorized. And as you can see, a model is actually parametric as soon as it doesn't have a static output. Instead, it can be modified geometrically with the help of user-defined parameters. And if you look in the model here, I have a rectangle, simple rectangle, and it is parametric because I can change the dimension of it, where the dimensions of h and b, I can change them independently with the help of parameters. Moving up in this parameterization level, I have equation-based relation, and here I start introducing relation between the parameters. Now looking at the example, I only need to control h, the height, because that one is independent, while the base now is a relation of height. Going forward, I have the script-based relation, where I start using knowledge-based engineering, and essentially start introducing intelligence into the model. And looking at the example again, I have now actually a new parameter called shape, and it's defined to control the geometry in the form of a conditional statement. Now, if you see that the shape, whenever it's given the value square, b and h will be equal, while h will be the value 10. Otherwise, we will have the same relation as before in the equation-based relation. Going forward, we have generic instantiation instead. And here we start involving the principle of adding and deleting features in your CAD model. Now this is actually the difference between topology and morphology, where topology involves, as before, to add and delete features, whereas morphology involves simply reconfiguring or changing your existing geometry. And that was what had been done in the three previous phases, three previous levels. And what I will do now, this is my existing geometry, 2 lines. And what I will do now is that I will add a rectangular surface, which is now partly coupled to my geometry because it's aware of the lower line, whereas the upper line is completely unknown for the rectangle. However, I can actually morph it now by changing its position with the help of user-defined parameters. And now I can change it along the line. Last step, the associative generic instantiation, is quite similar, the principle, to the previous level of generic instantiation. The difference is that the pasted geometry, the one that you put in to your geometry, has much higher or better associativity or connectivity to your existing geometry. As before, my existing geometry are 2 lines. What I will add now is 1 rectangular surface, which is also aware of, or fully coupled to my existing geometry because it's both aware of both the lower and the upper line. And as before, I can actually morph it, change its position with the help of user-defined parameters, as you can see here. And another word for knowledge-based engineering is simply model intelligence. Going forward, my theoretical framework also involved looking at what existing methodologies have to say about parametric CAD modeling. And from these methodologies that I found, it was that in order to have a clear, you have to model with a clear and a systematic modeling strategy in order to create a model, parametric model that is value-adding and functional. And you have to create a clear and systematic strategy in order to create and promote a clear and standardized model structure. And one way to have a clear and a standardized model structure is, for example, to divide your model into subgeometries, which can be seen for the example radiator tank model. Now, from these methodologies, I found out that there are a consensus that a designer must model with a clear design intent in mind. And this refers to how the model is intended to be structured according to its designer before it's even created. And also it refers to the level of awareness that a designer has of his created CAD model. Now the approach I have chosen involved both a theoretical and a practical investigation. Whereas theoretical investigations such as finding existing methodologies and the definition of parameterization were combined with practical investigations such as interviewing design engineers and also releasing questionnaires to the design engineers. Now, those two form eventually my foundation for my method development. And the method development consisted in turn of formulating modeling strategies, which you see now, modeling strategies, and these were then implemented on the case study. And by implementing it on the case study, the strategies, I also got a generated outcome, which I evaluated. And these outcomes were then documented in the purpose of forming my methodology, or as Scania would call it, a design guideline on paper. Now then, the entire methodology was then analyzed with respect to how compatible it was to the design process at Scania, but also how efficient it was in parameterizing CAD models. Now my result is divided into 2 parts. First, I will present to you the developed methodology, which I have developed in Scania, and then I will present to you the result of implementing it on my case study. In between, I will show you or demonstrate to you an Excel interface which is coupled to my CAD program, which is called CATIA. And this Excel interface was actually developed by my supervisor at Scania, and me and this second thesis worker, Marcus Bloomberg. Now, my development methodology consists of 3 phases, where I have first the pre-CAD phase, where I start preparing the model and establishing the essential information about the CAD model. And this includes fixed interfaces, which are connected to my parametric CAD model, and also the design requirements for the component that the CAD geometry will represent. And this includes manufacturing requirement or simply strength analysis requirements. But then I'll move on. I will use that information that I generated from the pre-CAD phase and implement it on the actual CAD model phase, where I create the model. This is followed by the model evaluation, where I evaluate whether the quality of the model is good enough for the future simulation. So the pre-CAD phase, as I mentioned, involved finding all the fixed interfaces and design requirements in the model. This is, but yeah, as I mentioned before, design requirements refers to manufacturing, production, or strength analysis. And with the help, by cooperating with the simulation engineer as a design engineer, I define what kind of transformation do I want to do with my parametric CAD model. Now these transformations are then translated into my parameters in the CAD model. Together with the simulation engineer, I also divide the model into smaller subgeometries. And that is done to enable the possibility to simulate or only analyze specific parts of my geometry, not entirely. Now that documentation or everything I find during the pre-CAD phase are documented in a document called a single document, specifically called the pre-CAD document. And that document is following the product or the component throughout its development process. And in the end, in short, the pre-CAD phase involves establishing the design space together with the simulation engineer and also plan for the coming modeling. And the CAD modeling involves implementing the generated knowledge or information that you got from the pre-CAD phase. And that is done primarily first by visualizing your interfaces for the CAD model. And that is done simply by having your CAD model and importing models that are connected to your model to be parameterized. Then the parameters that you have agreed together with the simulation engineer to create are created in the CAD model also. Lastly, in order to save modeling time, I also propose to find repetitive or similar features in your CAD model. Looking at the turbine volute, I see that I have a clear symmetry plane between my scrolls. And what I do essentially is that I use that property and model only one scroll and then mirror it to the other side of the symmetry plane. Therefore, I only need to model half of it. Now this component, we see that the pink object and the yellow one are quite similar in structure. And therefore, I only need to model one of these objects, copy it, paste it back into my model, and reconfigure it if needed. Now this model was created by Marcus Bloomberg, and it was supposed to represent the intake ports to the combustion chamber of an engine. And in order to promote standardization, structure, and reusability, it's important to follow the division of the subgeometries, which I hope that you remember from the pre-CAD phase. And this is done exactly for the turbine volute. We can see that we have three clear parts. We have the inlet, and we have the tongue section, which highlights the tongue-like section here. And then we have the actual volute itself. in order to make other designers to understand your CAD model, these divisions of the subgeometries are also highlighted in sketches, such as this one, and these sketches are then included in the pre-CAD documents. The creation of the CAD model goes through 3 phases, where we have first the skeleton model, or the wireframe model, as you would like to call it sometimes. And this is the model that you use to control your entire model. It is basically as a skeleton in a human being. And using that one, we create an enclosing surface by using the elements in the skeleton model. And in turn, by using the surface model, I create my solid, which is the final product. Now it may seem that it was quite a small step from the surface and the solid model, but generating the solid model is quite important to check the quality of your surface model, because it's not possible to generate this model if the quality of this surface model is lacking in the sense of that there are gaps in the surface model, and gaps, the simulation engineer hates gaps in their model, and it's important to rectify that. Now a little bit about the CAD modeling of the turbine volute. Now the most interesting part is that is the volute itself, the sub-geometry. And here you can see that it's built up by 7 different sketches. You can see here the first one being that, second, third, fourth, sixth, and no, sorry, 1, 2, 3, 4, 5. Yeah, the 6th and 7th. And now you can see that they're quite similar actually in structure. And that is because they're actually scaled down versions of themselves. Whereas the biggest one is the first one and the last one is the smallest one. And then these 7 sketches are placed in a fixed position along the circular outlet of the geometry. Now why 7? I will explain to you now with the next slide. Because I don't actually want to steer or control 7 different sketches independently. It would be a lot of control for just a single model. I instead create a graph representing the area distribution. Then, because I know that the sketches are fixed along the rotation, as I mentioned to you before, they can also use this graph to find which area they need to assume by reading the graph. And this is the input for controlling the area of all the 7 sketches. The graph in turn are controlled by 2 control points, which you can drag up and down to create different distributions. Now the sketch itself is controlled not by multiple dimensions. Instead, it's actually controlled by a single reference value, which is the height. And all of the small dimensions inside the sketch, the details, are all coupled with the reference value. So when this increases, so does dimensions in the sketch. Now finally, when the model has reached completion, I step into the model evaluation phase. And in the model evaluation phase, we use the Excel interface to conclude whether the CAD geometry is good enough. And what this Excel interface does is that it generates geometries inside my design space and it highlights models that fail to generate. And what a designer can do is to analyze these failed geometries, find out what is the cause of the model errors, and eventually, hopefully, fix the model. Now, if that's not possible, the designer has to actually change, reconfigure the design space slightly. Now, the Excel interface can also be used to take pictures of each geometry, and by putting these together, I can create an animation, which you will see in the next slide, of the turbine volute. And now you can see the flexibility of the turbine volute. Yes, and that's it. And now I would actually like to demonstrate to you the Excel interface. I'll just remove this one. I'll change to my computer. self-interface is actually used to control and evaluate the CAD model, as I mentioned to you before. But it's also used to contain the information that you gather from the pre-CAD phase. And as you can see, the Excel interface is an Excel sheet, not so surprising. And as you can see that the Excel interface consists of a number of sheets, where the green sheets, which are these ones, represent the information that you gather from the pre-CAD phase. But firstly, and then you continue with the orange sheets, which is the model evaluation phase. So let's continue, but let's start from the top. We have the information sheet, and here we just highlight the name, the article number, or the project the model belongs to. Standard introductory information. Then we highlight the interfaces of the camshaft, of the model, which in this case is actually a camshaft. We also have a company's reference model to see what kind of model we're talking about. Interfaces to the camshaft. We have which people are interested in the model, and here we see the CFD, FDM, assembly, processing, aftermarket. Design requirements are highlighted here, and you see here each requirement are coming with a short description of what it means. And then we have what's called parameter definition matrix, and here we highlight which parameters that we want to change in our CAD model, and also as in the design requirement, they have a short description of what they need, and also a min and a max value, and a reference value representing the reference model, and together these values represent the design space of my model. Furthermore, we have the PRM, the parameter relation matrix. Here we highlight if there are any relations between the parameters that we have established. And that is the entire pre-CAD phase. Now let's see the model itself. You can check this is the camshaft, the model. And we can see that the parameters are also in the CAD model, which we established in the pre-CAD phase. So for example, I have shaft radius as in my PDM, the shaft radius. And we can see that there is actually a bit of a repetitiveness here. We say that this section is actually repeating as in a camshaft, and this property is used in order to shorten the modeling time. We only model the first part and then copy it, instantiate it back, paste it back into the model, but with a different position. Alright, enough about the model, and let's continue with the modeling phase. And it's called the DOE because it stands for Design of Experiment. And design of experiment means it's an experiment that you try to investigate what parameters are having, what effects do each parameter have on the CAD model. And here we have some introductory stuff that we have to fill out, like such as in the name of my CAD model. So my CAD model is called example shaft, example underscore shaft, and we have the format as well. Here we are. We need to establish where we want to place our results. And I'm going to create a new map here called demo 2 because I would have demo. There we go. And then we can define what kind of results we want. And as before, I would like to have screenshots. And we can choose how we want to sample our design requirement, the design space. And here I will choose Latin hypercube because it evenly distributes these design points in my design space evenly. And now I also define how many design points I want. Of course, the more you sample, the better will the approximation of the robustness in your model be better. But because it will take quite a long time if we put, for example, like 1,000 design points, it will take quite a long time because my computer is not the best. I will actually just put, let's see, actually 10 I think is quite good. And here we can also see how many geometries have failed and which geometries have succeeded in generating. And then, according to high school math, you can also calculate the robustness. Right? by using that information. I also want to import my parameters for my Cartesian model. And this is done by simply checking first what kind of results do you want to have. And the parameters that you don't want to import is simply hide. For example, I don't want to have this one. I hide it. Here we go. And actually I want to rest. So that's finished. And then I press this button. Here we go. My parameters, they are 12. And then I have to manually put in the number minimum value and the maximum value. But in order to not bore you to death, I already done that before. So I copy that. And I paste it. There we go. And then what I need to do now is simply, now you can see that each parameter has been also updated in the Excel interface. I have my parameters in columns here. And now each row after that represents a design point. And what we'll do now, because I have determined that it should be 10 design points, it will be 10 rows. So let's try it. Generate design, 10 design points. And now what's left to be done is to save the geometries. And that means generating the geometries that you have in this design space, the design points simply. So let's try. Save geometry. And now you see that it counts like 1, 2, 3 of 10. And then you can see the model is maybe hopefully robust enough to show the update, of course. Great. Maybe I have time to show you how the model demo to picture of we finished. 10 geometries. And go in and check each model. Great, and we got 10 pictures, which means that the robustness was 100%. And that concludes the demonstration of the Excel interface. I'm going to change that. Also, my results, let's see.
Välja displaya detta.
Det kommer vi se.
Är du i presentationsläge på kartan?
Nej,
Prova det.
Okay. So continue on. My results also involve evaluating the model, the evaluation phase of my case study. And that refers to the robustness, the quality of the model, how robust it is in its design space, how much time did I invest in creating the model, from preparing it, creating, and evaluating it. Lastly, I also checked or analyzed how compatible my methodology is to the current design process that's going on. So in other words, how familiar is the methodology as of today? But starting from the top, my Camel, the turbine motors, it reached a robustness of 97%, finally, in its given design space. But this percentage was actually only possible by conducting 2 prior model evaluations. So from the beginning, I have a robustness of 80%, approximately, which is not so good actually. But that result was used as a basis to look at what caused the errors in the problem. And then I went to the model and fixed these errors. So then I went and conducted another evaluation. But I reached actually a lower percentage, about 80% still. But repeating the same procedure again, I reached a percentage which was satisfying. Looking at how much time I invested approximately 75 hours in preparing, creating it, and evaluating it, where the majority of the time went into modeling the CAD model. And this unproportion, let's say, is explained by the fact that Scania, as I mentioned before, had no prior experience or knowledge about modeling such components. And as for myself, I've never modeled such geometry before. And this meant that I had to actually find different modeling strategies and choose or pick the most suitable one. Now, comparing, well, this analysis is different from the one I have in my report. And it's a bit lower here because in my report I included the time it took to create external features in my CAD model, which I have not done here in the presentation. Now, what I actually concluded is that much of the methodology is actually something that design engineers already do during their daily work at Scania, such as finding information in the pre-CAD phase, finding information about manufacturing, design requirements, strength analysis. Also, working with simulation engineers to optimize the component is nothing new to them. What's being introduced is documentation of this information in a single document. Now, using the result from the questionnaire, I also find out that the design engineers already reflect and plan upon their structure in that model. Also, they know how to solid and surface model in the CATIA. What's being introduced is the reuse of the geometry using, for example, power copy or copy-paste. Moving on, also we know that they know how to reconfigure the structure of the CAD model, because we know already how the development process is between design and simulation. What's new here instead is the evaluation of the model through an automatic testing through the Excel interface. Now these elements that are new are covered in the methodology, excluding the last one. The last one is only included in the methodology that has been presented or introduced for Scania. Now, with the methodology, it's much easier for a design engineer to create parametric CAD models. Now, this is the update of the development process. So now, the design engineers will create a parametric CAD model, combine it with the Excel interface to create a big set of geometries, which can be simulated, evaluated, or be concluded to be improved designs or not. And by simulating more geometries, comprehension and optimization of the component can be done much faster than previously. So finally, my conclusions. Starting with the first one, what are the benefits of using parametric CAD models? The main benefit is the rapid identification of improved design models using simulation results. And by doing so, you also get a deeper comprehension of the component by analyzing said simulation. The standardized structure of a CAD model also means that it provides a common bridge between design and simulation regarding, most importantly, modifications. Because now, modifications can already be done in the CAD model instead of doing it in another software which is completely unknown to the designer. And referring to the model's flexibility, the model is reusable to become other components, similar looking components, but it can also be reused in the sense that it can be reused in other projects. Moving on, in what instances are the models compatible? Whenever it's compatible, whenever you want to or have to explore different designs. And whenever you have multiple stakeholders involved in the same model. Now, stakeholders refers to not just simulation engineers, but all kinds of people that are interested in your model, in the parametric nature of the model. And then it can be, as shown in the Excel interface, it can be firm, it can be subcontractors, it can be the production engineers. Also, by having a standardized structure in a parametric CAD model, collaboration between the design is amplified or much better than before. Also, so in the end, there is actually no explicit case when parametric cameras are not suitable to use. Maybe one such really specific case is when you want to create and use parametric cameras in the purpose of optimize a component when the time frame of the project doesn't allow that. However, in the end, whether a project is short or long, whenever there's a desire to modify your geometry fast, parametric cameras is the price. What are the challenges? The main challenge that I see is the organizational resistance towards the implementation of parametric cameras. And that means to break through the resistance. And in this case, resistance would be rooted in the fear of the unknown based on lack of knowledge and awareness of such models. And this brings out the importance of really spreading out the knowledge about parametric cameras and also revealing and showcasing what benefits these models can have for a design engineer's work. Another challenge is limiting the total amount of parameters and reference elements to a minimum. And that brings out really the importance of having thought through and reflected upon your structure before even realizing it in the software. Lastly, creating a model which transforms morphologically and topologically as expected by the simulation engineer on the first attempt is something not to be taken lightly, this challenge. And this really emphasizes the importance of having a good communication between yourself as a designer and a simulation engineer. The risk would be, if you don't follow that, is that you create a model which is really good, high quality, robust, flexible, everything, except that it doesn't fulfill the modifications that the simulation engineer desires. And lastly, how should Scania work with parametric cameras? I have two answers for that. For short term, I feel that parametric cameras should be applied on all kinds of pre-development phase projects, because these kind of projects have the design freedom and also the time frame to allow such parametric cameras to be used for optimization purposes. But most importantly, these kind of projects enables the design engineers to really learn how to use these kind of parametric cameras. So therefore, my answer to a longer term is that they should be applied on all kinds of projects. Because really, you cannot reach and modify geometry faster than with a parameterized one. Now, all these really benefits can only be reached if the methodology that we have, or I have proposed for Scania, is feasible to the design process. And because the methodology was developed with the design process in mind, it is also applicable to the current design process. Thank you for your attention.
Thank you.